Welcome back. So in this lecture, we're going to be talking about Newton's method, which is probably the most, if not one of the most useful methods or used methods in optimization. All right, so first we'll recap a bit of gradient descent to make a comparison. So as you remember, we want to optimize this problem over here. Yeah, so minimize some scalar function. And we start here, and through an iterative procedure, we want to get to the optimal over here. And the idea is that this was gradient descent, right? The algorithm that we saw that didn't perform that well with some step size and some direction. Again, the gradient includes not only a component in the direction, but also a component in the step size, but we just assume that the step size is absorbed by this by the step size component alpha. Yeah, and the idea is that this didn't work very well, and now we're going to see an alternative, which is Newton's method. Yeah, so passing on to Newton's method. So what's the idea? So gradient descent was this method over here, and what we do in Newton's method is change this alpha, which is a scalar here, by a matrix. And this matrix is going to be the inverse of the Hessian matrix. Yeah, so the inverse of the matrix of second derivatives. So again, the idea here is that at any point xk, we're going to compute not only the gradient, but also the Hessian. And then we're going to use the product of the inverse of the Hessian and the gradient to optimize our system. And now the idea here is that this is going to allow us to capture the curvature of the problem, and this will help us converge very fast to an optimal point. But the question that we want to ask ourselves is, how do we know that this is a decreasing direction, right? For the gradient, for steepness, for the gradient descent, we knew that it was a decreasing direction because, again, at least in the very vicinity of our current point, we were going in the direction of the fastest decrease of the function, or our gradient was equal to 0. Yeah. But here, the Newton step, how do we know that this is actually going downhill, which is what we want to do, instead of going uphill or just going to some random direction, which is neither? So the idea is that we will use so we will analyze this, which is our step size, right? So if you see, we have xk, and if we add this delta x, this is going to be our step size. Yeah. And what we want to have is that our directional derivative is less than 0. Yeah, so from calculus, if you remember, if you have a function, and then you get the gradient of that function, and then you multiply that gradient for some direction, or some step size with a direction, then this would tell you how much was the function, if the function was increasing in that direction or decreasing. So what we want is that the directional derivative is negative. Yeah. So that means that this direction that we're computing, which is this direction over here, which is itself our Newton step, this is going on a negative direction, on a decreasing direction. Yeah, which makes this term negative. And then what does this term translate? So what we're going to do is, here we have the gradient of our function, but now we substitute this term over here. And the idea is that we wish this whole term to be negative. Yeah. Again, what we're trying to find out here is if this Newton step is actually going downhill, because this is what we want. Yeah. And so what we'll see is that this is almost, well, not all in. So what we'll see is that in convex problem, this is a decreasing direction. Yeah. And for this, we see that, well, if we have a positive definite Hessian, well, this is a positive definite inverse of the Hessian. This happens if our Hessian is positive definite. Yeah. So we want the inverse of our Hessian to be positive definite. And why is that? Because from the definition of some matrix being positive definite, so in this case our Hessian, we know that if we multiply it by two vectors, by the same vector from the left and from the right, then this term is always going to be bigger than 0. Yeah, if our Hessian or if this matrix is positive definite. And that means that then, because here we have some vector from the left and from the right, this means that this term is always going to be positive, and then with a negative sign here, this is always going to be negative, and this means that our Newton method is always a decreasing direction. Yeah. So the point is, when is our Hessian positive definite? Where our Hessian is going to be positive definite whenever we have, whenever our problem is convex. Yeah, whenever we have convex curvature. And the idea is twofold here. Most of the time, when we're near the optimum, our Hessians will always be positive definite. And the idea is that most algorithms that implement Newton's method have ways of determining. So what they do is they determine if this matrix is positive definite, and if it is, they just proceed. If it's not positive definite, they generally turn it into some positive definite matrix, most of the time simply defining the closest, under some measure, the closest positive definite matrix that is similar to the Hessian. Yeah. So again, the main picture of this is that we're going to be, Newton's method is defined by this step, which instead of alpha has the inverse of the Hessian. And how do we know that this is a decreasing direction? Well, we know it by using the directional derivative in the direction that we're moving on, which is this direction. And we see that this direction is always going to be decreasing when we have a convex problem, or when we're near our optimum, which itself is like a convex, it has some convex shape. And this is going to be most of the time, but in non-convex problems like we have in engineering, physics, or machine learning, it's common that the curvature is not always positive, so you might have Hessians that are not positive definite, and in that case, most algorithms have some schemes that simply make the Hessian positive definite. Yeah, so they grab the Hessian and manipulate it as little as possible, so that such that you have practically the Newton step, but with a positive definite matrix, right? Okay, now we're going to talk about what does this mean. Why are we taking the inverse of the Hessian and putting it in the step size? So the idea is that the first interpretation of the Newton method is that we're minimizing a quadratic approximation of our function. So what does this mean? So this means that we have our current function, and we say, so I'm going to do a second order Taylor series approximation of my function at my current point xk, and for my step size. Yeah, and this is my second order approximation of my function, and this is a quadratic function. And the idea is that then by minimizing this function, I'm gonna get delta x. Yeah, and this is the direction that I'm gonna move. And this, so I borrowed this this picture from the book of Convex Optimization, and the idea is that, so the solid line here is our function, and this dashed line is our approximation. Yeah, and this is our current point. So the idea is that around our current point, we make a second order approximation, which is this one over here, and we minimize that second order approximation. And that's how we get our new point. And then around this point, we would make another second order approximation and minimize that point again. Yeah. And that's equivalent to Newton's method. Yeah. And you can see that if this term, you get the derivative of this term, yeah, this term goes away. Here we're only left with this gradient term, and then for this term goes away, and then you simply pass the gradient to the other side because you want that to be equal to 0. Yeah, because again, you're trying to find where the gradient of this term is equal to 0. You pass this one to the other side, which gives you the negative sign, and then you have to pass the Hessian as the inverse, and then you're left with this delta x being this term over here. Yeah. Okay, so this is the first interpretation. And some interesting thing is that when we're getting near an optimum, particularly a well-defined optimum, our function actually looks quadratic. Yeah, starts to look quadratic. And the idea is that very close to the minimum, our approximations are going to be actually very, very good. And something that we'll see is that Newton method converges to the optimum particularly fast when it is actually near it. Yeah. Okay. Now, the second interpretation, again, we remember that we're trying to find where the gradient is equal to 0. Yeah. And the second interpretation is that we're gonna do now a first order approximation, but of our gradient. Yeah. So that means that again we have our function plus the derivative of our function, which then the derivative of the gradient is Hessian, times our step size. Yeah, and we want this to be equal to 0. And again, we see that then this is very obvious. So this gradient, we pass it to the other side as a negative. Yeah, so this is where this minus gradient comes into play. And then this Hessian goes to the other side as the inverse. Yeah, and that's how we get our next step size. So again, these are the two interpretations. So one of them, so the one that we saw last time, is that at every point we're going to be solving the approximate optimization problem by approximating our function by a quadratic function. And then the second interpretation, which is this one, is that we're actually going to be approximating the gradient of our function by a first order approximation, which is this one, and solving it at every step. Yeah. And again, here we have that interpretation where the solid line is our gradient function, and our dashed line is the first order approximation, which you can see it's a line. And again, this is our point where we're going to do the approximation. And that's where you do the approximation and you find where this crosses 0, which is this point, which in our true function is this one. And then here you would once again make a first order approximation, which is again a line, and you would get very near the next point. Yeah. So these are the two interpretations of why we're using Newton's method. And the algorithm, as we defined for gradient descent, would be very similar. So you start at some point x0. So again, this is our starting point, and then you break when your gradient is small enough, right? And then the idea is that again, at every step, now you not only calculate the gradient, but you also calculate the Hessian and the inverse of the Hessian in particular, and that's how you get your next point. Yeah. Now, some little differences that most of the time you won't be using the gradient as a measure, but you will be using actually the Newton, which is called the Newton decrement. Yeah, which is simply this directional derivative. And this is just a better measure of how close we are to the optimum, particularly for the Newton's method. Okay, so what's the performance of Newton's method? So the idea is that because Newton method is able to capture the curvature, yeah, so you're actually, because again, you're doing a second order approximation, then you can see here that, for example, while gradient descent goes all the way around the curvature, Newton's method is basically able to know where the optimum is before the gradient descent, and it goes directly to the optimum. Yeah, and again, I think I remember for this one, gradient descent did something like 60,000 iterations. I think Newton method does something like 4. So again, it's much faster. And again, here is just for our quadratic problem. So because the problem is quadratic, obviously Newton method just goes directly to it, while gradient descent zigzags a lot. Yeah. So again, the performance of Newton method in iterations is much faster. Now, a disadvantage of Newton's method is that you're actually using the Hessian. Yeah. And this means that you have to compute second order derivatives. And in applications where you have many variables, so let's say where you have billions of variables, like in machine learning, you don't have the memory to compute a Hessian. Yeah, I mean, there are intelligent ways that you don't compute the Hessian all at once, but still this is very expensive. So that's why in many cases, particularly in the machine learning community, they're not using Hessians. One other disadvantage of Newton's method is that, again, the Hessian might not be invertible, and this happens in non-convex problems. This is easily fixed, yeah. And again, there are also other methods like what are called quasi-Newton method, which approximate the Hessian such that it's always positive definite. And again, the problem is that it's expensive. Yeah, obviously, because you're also multiplying a matrix times a vector every step. yeah, because you're multiplying this inverse of the Hessian times a vector. This is expensive. So although you have much less number of iterations, every iteration is much more expensive than a simple gradient descent. Now, for most engineering applications, Newton's method is just so much better than gradient descent, then still you have to go for it. So, I mean, just general advice would be always try Newton's method as long as your memory can allow it. Yeah. So some nice takeaways from Newton method is that it's not really affected by scaling or ill conditioning. So when we saw gradient descent, we saw that when actually we had a higher variation in one direction than in another, gradient descent performed very badly. So Newton method is completely unaffected by this. The calculation of derivatives and actually because of the numerical routines that you have, they might be, but in theory, Newton method is completely unaffected by this. Yeah, it's a second order method, so it uses gradients. The error decreases quadratically. This means that the error for, again, let's assume that this error is less than 1. The error, for example, at one iteration is equal to the error at the past iteration squared. So this means that once your error is small, actually you're going to go very, very fast to the optimum, right? Let's say that, again, your error is e to the minus 3. Then at the next iteration, your error will be e to the minus 6. Remember that gradient descent was the opposite, right? When you were getting very close to the optimum, actually your error, you started to make very, very slow progress. So this means that Newton's method is very good for high precision. And it's actually also used in practice. Yeah. So something important that I should mention is also that generally you don't really compute the inverse of the Hessian. Generally, what you do is solve some linear system, and there, I mean, all of this, they're very robust linear algebra routines to do all this, and their whole course is on Newton's method. So this is basically just the main and high level ideas of their properties, but this is also enough so that you might go to your favorite coding or programming software and code your own. Yeah. So again, this is the big idea.